one you're starting to use, PyCharm or whatever. For turtle programs, it's not such a good idea to try to do it online. There may be an online version of Python that supports the turtle drawing, but we may as well just use it here, huh? So we're really only on Lecture E. I guess that's because we missed 2 days. We had a snow day last Wednesday, didn't we? Alrighty. That's why we're only now starting Chapter 2, but that's okay. I'd rather take our time and learn the material well. Alright, so this is Lecture E. We're going to do a little bit of turtling, and then we're going to draw a module, or create a module, which Python calls a function, which also, uses turtle to illustrate a programming concept. So if you feel like typing along, and I hope you do on this one because it's kind of fun to draw things on the screen, right? So we are beginning Chapter 2, so I'm going to add that as a comment here, even though that's not the first thing we're going to hit. So Chapter 2, an example of turtle graphics. All right, so to get the turtle to work, we have to import the turtle library. Oh, and since we have this up, come on, enter key. Oh, come on. There he is. There's the turtle, right? Like that. You can kind of see the idea. It's got wheels. It's not a close-up, but hopefully we could get the idea that it could extend a pin and retract it to draw pictures. So you import the turtle, and then you have to create a turtle variable. Instead of just doing something like t is equal to 1 or whatever, we got to call a function in the turtle library that creates the turtle object. And so I need to give a variable name. I just could call it t, right? But I'm going to call my turtle Leo. So Leo is equal to turtle, and now I have to call a function that creates it. And what you're going to see here is a syntax that's an example of objects, object-oriented programming, meaning that here's a library, but we're going to create an object from it. And to do that, you have to call a function. And in this particular case, the function call begins with a capital T. So turtle with a capital T. The whole word turtle in front of the dot's lowercase, after the dot capital T, parentheses in parentheses, because all function calls, all module calls end in parentheses. And that makes our turtle. Let's prove it. Leo dot, now I could type the whole word forward, but whenever I do, somebody misses the R or something like that, and so I'm just going to type FD, the abbreviation, and I'm going to send the turtle forward 200 pixels. Then I'm going to make the turtle turn right 90 degrees. And because I'm lazy, I'm going to copy those statements and paste them 3 more times. Why? Because I want to draw a square, right? 90 degrees will draw a square, but you need to draw 4 sides. So if I copy those and paste them, Control V, that's side 1, side 2, side 3, and side 4. So when I run him, there he goes. That's pretty cool. Let's do something else. Let's make this a module so that we can draw a square anytime we want with a single word. Because that's the idea behind functions, behind modules, is you pack up a whole bunch of code into a single word so you can use that word to trigger it. It's like rather than me giving you a whole series of steps to go to Walmart, I just say go to Walmart and you know how to do it because you already have the series of steps memorized or whatever. So to get that to happen, I have to define my function. I have to define my module. And so you use the DEF keyword. And I'm going to call this module the very creative name square. And like I said, all function calls, all module calls have parentheses in them. Same thing when you're defining them. And to mark that all this code is inside the module, I need a colon. So it's DEF square, parentheses in, parentheses, colon. And then all this stuff has to be tabbed over one. Now you don't have to tab it like this. You don't have to do 1, 2, 3. You can highlight a whole bunch of lines at once and then hit the tab key and boom, it moves them all over. All right, fantastic. When I run it, nothing happens. Right? It's like I wrote down a recipe, but I didn't ever tell anybody to bake it. I have to call the function before it does anything. You can define functions all you want, but until you call them, nothing happens. So down here, I'm going to call the square function. Square, parentheses in, parentheses. So when I run the module, now it does draw the square with one call. See that? If I wanted to draw the square again, I'd just call square, right, a second time. That's kind of pointless because it's going to draw the same square, right? Not so cool. But we can do something else with it. All right, yeah. And we could put it in a loop, right, and it'd draw the square over and over and over, but that's kind of silly. Instead, why don't we turn a little bit before we draw the square again? That way we can at least see it drawing. So between these two calls to square, maybe I'll turn, whoopsie. I wanted to insert it between them, not between the parentheses. Let's send Leo to the right, maybe 45 degrees. So this is how you define a function, define a module. The book calls them module. Every programming language calls them functions or methods or procedures, but since every language calls them something different, the book gives them the name module. So define the square module. And what is a module? What is a module? What is a function? A module is a named block of code that can be called, although you'll hear the fancier term invoked, can be called to perform a task. In this case, to draw a square. So now when I run my module, it draws it, it turns 45 degrees, and it draws it again. Now that's pretty cool. So if I did that 8 times, it'd draw a pretty cool looking shape. So I'm going to copy those two statements, the call to dot right and the call to square, and paste them a couple more times. How many squares do I want to draw? 8 total, and I have 2 on the screen. So after I copy it, I need to paste it 6 more times to draw 6 squares. Again, I'm Control V-ing for easy pasting. How many have I put in here? Square 1, square 2, square 3, 4, 5, 6. I need 2 more. 7, 8. All right. Off he goes. Man, neat. We should write a program that'll draw a Triforce. Nah. But anyways, so that's the idea behind functions. We wrote a function that drew a square so that we could draw a square with a single call. Now the next thing that I would want to do if we were going to continue this example is to make it to where the square could change in size, right? That square kind of went off the side of the screen. And yeah, how would we change the size? Well, the easy way would be to come in and like edit all those 200s to 150 or something like that. But what if we wanted to be able to change the call every single time we call the square function? Now, like I said, I'm not going to, well, you know, I've talked about this enough that maybe I will. Let's make it so that we can do this. I want a square of 100 pixels, right? That's what I want to be able to do, but it's not going to work if I do that. And I'll walk around in a minute and make sure everybody's got this going. Because our function is not programmed to accept that argument. That number between the parentheses is called an argument. We need to define a parameter variable that will accept that argument. We're going to have to modify our function because you can't pass in a number down here if there's nothing to catch it up here. It's like throwing a ball without anybody to catch it. So why don't I call my variable up here, and I'm editing this line now, to add a parameter variable called size. And I need to replace all of these 200s with size so that, you know, when I call it, the number of pixels that goes forward each time is based on that variable. So save yourself some trouble and copy that. I hope you know that if you double click on a word, it highlights it. And so then you can just double click on all these 200s. Leave those 90s alone because we still want it to be 90-degree angles. All right, so now drew a smaller square. But the rest of these calls are broken. And it says line 27. What have I done wrong? Well, I need to find line 27. Figure it out. I mean, you can probably already guess what's wrong, but I'm showing you this because right now the cursor, the line number right down here is line 24. So I'm going to move down here until it says line 27, and I'm going to see the line that's wrong. Ah, well, since square requires an argument to fill in this parameter variable, I'm going to have to type in a size here. How about 100 there? Or how about 90 there? And an 80 inside the next square call. And a 70 inside the next square call, and so on. A 60, a 50, and a 40, and a 30. How about that? So each time he draws, it's going to be a smaller square. Kind of a conch shell shape. It's kind of cool. Anyways, if you don't like that, you could change all the square calls to have the same argument, right? To pass in 100 each time. Now here we have an example of repetitive code, right? I copied and pasted. Whenever you're copying and pasting, think to yourself, could I make that a loop? Right? Because with a loop, I probably could have written a loop that counted from 1 to 8 and then just called the square function and a right turn, and that loop would be 3 lines long to do the same thing that all this did. Why would you want a loop? To perform some repetitive task. What if I wanted to do that, draw 100 squares on the screen? I would not want to copy and paste these commands 100 times in a row. Instead, I'd want to write a loop that called the square function 100 times, and it might just be like 3 lines of code. Or there's an algorithm that calculates pi. Sounds weird to calculate pi, but you know, there's an algorithm to calculate it. And it's an iterative algorithm, meaning that it repeats over and over and over until you get pi out to the precision that you want, the number of digits that you want. Well, that requires a loop to iterate over and over and over. But you could write the algorithm so instead you just copied and pasted the line. But to calculate pi to any fair degree of accuracy might take 1,000 times. And I would not want to copy that algorithm and paste it 1,000 times in my code. That'd be silly. That'd be ridiculous. Especially if you made a mistake in it, right? Then you'd have to correct it 1,000 times. That'd be real annoying. All right, so let me go around and make sure y'all are doing okay. And if you ever need me to scroll back up and show you something that's off the screen, please ask me during a lecture rather than wait until the end. Whoops. Let's find out. Well, that didn't work. So turtle with capital T. Let's try that. And by the way, if you run the program over and over and over and you get tired of the turtle moving so slowly, you can speed it up. I'll show you how. Well, okay. I'll research that later. I'm not getting it to work, but that's okay. If you want to speed up your turtle, then right after you call it, scroll up here and say leo.speed like 10. 10 is, this number is the delay. 1 is the slowest, 10 is fast. Now if 10 isn't even fast enough for you, if you set it to 0, that means absolutely no display at all, no delay at all. Yeah, I like that. That's better. All right. I didn't get to the back of the room. Let me see how the rest of y'all are doing. All right, so every time I unpause it, you see this statement pop back in some various form. The problem that we're trying to solve is that if you're using PyCharm, it doesn't seem to be popping up the window or keeping it open or something like that. And so we're playing with trying to get that to fix, even though we're not using PyCharm, or at least I'm not on the screen. Some students are. Give that a shot. Did it work? Did it keep it? Okay, well, I'll have to do some research. What does turtle.done do anyways? Let's go Google that. I'm going to go through that a little bit more slowly. What did I do to find the answer to what I'm looking for? I just typed in turtle.done into Google and hit the top link because it says it's on the Python site. Sounds good to me. And then since I'm looking for the word done, I'm going to Control F, or Command F on the Mac, type in done, see what it does. Done. Calls a main loop function, must be the last statement in a graphics program. Must not be used if the script is used from within idle in -in mode. All right, so what's that really doing? It's waiting for me to close the window before it finishes. Notice that these cursors right here don't show up until I actually close the Python window, and that's because of the done command, right? If I delete this or comment it out, then the program runs and finishes. Doesn't wait for the window to be closed. Okay, I lied. I don't know what done does. That's what I figured it did. I'm wrong. I'm going to stop talking about done because clearly I'm done with it. Yeah. I'm so over it.
You need to hit the stop key or the stop button.
Yeah. Okay, so we have an example of functions, of modules. We've made a pretty powerful one in as much as you can customize its behavior just by passing in a parameter. Turtles are cool. You can change their speed. You can lift the pin. You can lower the pin. You can set the thickness. You can change the color of it. You can change the shape of the cursor, right? So instead of being a triangle, it's actually a little teeny tiny turtle. So it's kind of fun, and we'll be going back to this concept because it's not only fun, but it's a useful way of demonstrating programming concepts. So as a reminder, the 100 is called the argument. Whenever you have a function call and it needs a piece of input, that's an argument. And up here, size is the parameter, or the parameter variable. So I'll add a comment to that effect as well. All right. On to lecture 2. Or not lecture 2, but chapter 2. Seems early in the semester to nominate me for a professor of excellence, but if you feel inclined, no, I'm just teasing. Alrighty. Elements of high quality programs. Declaring and using variables and constants. We've been kind of doing that already. Performing arithmetic operations. The advantages of modularization. Well, since we've already seen variables, let's learn about constants. I have this number that's repeated over and over in my code. Right, at 90. What does that 90 mean? It's the angle. It's the angle of a square. It's a right angle. So, I'm going to come up here and I'm going to define a constant. And I'm going to put it in all caps just because the convention among programmers, kind of the agreement, gentlemen and gentlewomen's agreement, is that if something is in all caps, it means a constant and the program shouldn't change it later. Well, why do we have that agreement? Because Python doesn't have a keyword that actually makes a variable constant. So I'm going to type in right underscore angle equals 90. Then I'm going to copy that and paste it over all the 90s in my code. Now, if I could think of a cute word for 45, like half right angle, that sounds silly, so I'm not going to bother. But anyways, you get the idea. Maybe this makes the code easier to read, right? Turn right and make a right angle. Okay, that's kind of silly because right angle makes it sound like it's turning to the right. You have to know the geometry, you know. You have to remember from trigonometry or whatever that a right angle is 90 degrees. But whatever, you get the idea. And if we change that to something else, like 45, it would change the behavior of the program, and it would no longer be drawing squares, so it would look ugly. But anyways, I'm going to give it a shot. Well, that's kind of cool. Kind of dumb, but kind of cool. Alrighty, so you get the idea. A constant is something that you define near the top of the program, usually at the very top, but apparently I didn't do that, and I'm not going to bother moving it. For a variable that's used over and over and would probably cause that program to malfunction if that variable was changed. Now, a common constant for people to use is pi. When your professor is as weird as I am and likes you calculating spheres and cylinders and circles and stuff like that over and over and over, then you would need pi. Now, there's a way to ask Python to give us a pi constant. If there wasn't, I could type this. Pi equals 3.14159. And then through the rest of my code, whenever I needed pi in my calculation, I would just put that word, right? Rather than actually type in that number. Well, why is that better? I mean, 3.14159, most people recognize that. It's not a mystery. Well, for one thing, it's not super duper accurate, right? Pi is an infinitely long number. 5 digits of precision after the decimal point, yeah, great. But maybe I'm sending a rocket to the moon and writing the code in Python for some reason. So maybe I need a better version of pi out to 8 digits or 16 digits or something like that. Well, if it's defined as a constant, I could change it in one place and it would affect everywhere in my code where I used it. Well, what if when I'm typing that number in over and over and over, I make a mistake? Like I type in 3.1459, right? And then another time I type in 3.1559, right? You know, fat finger it. I'm goofing up. Well, then the calculations are wrong and I might not be able to visually see it, right? Whereas if I put it up here and then I reuse it, then if it's malfunctioning, I know where to go. I know that I just need to change it one time. So these are constants. They're used to replace what are known as magic numbers. That's a nickname. But that 90 degrees, I'm changing that back to 90 to actually make it look like a good. If I didn't know anything about geometry and I didn't know why it was turning right, there's more than one way of expressing degrees in geometry. There's a system where there's 360 degrees in a circle, but there's another one called radians, right? And 90 degrees in radians, I don't even know what it is. Yeah. So what if, don't make this change because it's not going to work, but what if every time I called right, it said that, 1.5708. Now, if you were a casual observer coming up to the code or somebody wanted you to come and fix it, right, that's called maintenance programming, and it's a common early programming job, or you come back to the code, 8 years later after you've written it, and you see these calls to 1.5, whatever, you might have no clue as to why you told the turtle to turn right that minute. But if it was defined up here, right, and then you knew, oh, I'm making a right angle, it doesn't matter what measurement system this is measured in, right? It's still readable. So it's a magic number because it appears in the middle of the code out of nowhere. Ta-da! I have no idea what that means, right? Tax rate could be another magic number, right? You're going through here and you see some reference to 9.25 or something like that. And so you don't know why that number is in there. And, mathematical constants, like there's one called Avogadro's number, 6.022 e to the 23. If you were going through some chemistry program and you saw 6.022 e to the 23 used in some formula, and you didn't know chemistry, you'd go, what the heck, right? And if it was instead defined as a constant, Avogadro's number, when you saw it in that formula, you go, boom, I know what that is. Or you wouldn't, you could Google it, right? And then you would know what it is. Let's change this back. So that's what a constant is. Define it up at the top of the program, put it in caps, and it's something that should not change during the middle of the program. I should not change the value of pi down here, right? Pi is a constant. It's a universal fact of life. If I can change the value of pi, then I have more powers in the universe than I ought to. Let's go back to the PowerPoint. So data types. Data types describe what value can be held by the item. Well, this is what's known as an integer data type because it's a whole number. I guess in math they call it a real number. Been a long time since I took
both.
Pardon me?
It's both.
Yeah.
Number and integer.
And this is a floating point number because it's got a decimal. So this is an int or an integer. It's just an example of that. The type is integer, int for short. And here the type is float. Float, parentheses, floating point, right? Every variable has a type. Even if we don't know what type it is, it's got a type. So far, our program only has 3 variables. Here's a variable. How do we know it's a variable? It's on the left-hand side, and then there's an equal sign. So this created a variable of type turtle. This created an integer variable, and that created a float variable. So I'm going to put a comment about variables. I'm going to open and close my triple quotes. Variables have 4 components, 3 of which really matter to us in this language and in most languages. Variables have 4 attributes. They have a name, right? Because if they didn't have a name, how would you get a hold of the data? They have a type, example, int, float. They have a value, although they can be undefined before you start using it in some languages. In Python, they're not undefined. As soon as you create your variable, it already has a value. That's not true of all languages. And then there's address. Where in memory is that data stored, right? Because your computer has 8 gigabytes, 16 gigabytes, whatever. The program has to know what couple of bytes stores that integer, and so it keeps track of the address of that variable. But we don't care about that usually. We can't even get a hold of that address in this language. There are a few languages that let you modify data by the address of the variable. You're supposed to use the variable name itself. because trying to change data by address can crash the program. What if you write to the wrong address? And so some languages like C and C++ do let you do that, but a lot like Python and Java and C# do not. I hope I didn't lie about C#. It's generally true. Usually you don't care so much about the address. These are the key things. If I ask you to name 3 attributes of a variable, those are the ones I hope you remember. So the name of the variable is important, right? Because if you don't know its name, you can't tell it to do something. You can't just go, hey, you, like we can in real life. I have to use your name to let you know what to do. The type is really important because it says what kind of operations can be done with that data. Right? If it's a numeric type, you can use it for math. If it's a turtle type, you can't. I can't say turtle equals turtle plus 2. That makes no sense. It's a turtle. I can't add numbers to it. Right? But I can add numbers to a numeric type, like an int or a float. So the type describes what kind of data it holds. It holds, and what kind of operations can be done with it. For example, and that term operation sounds all fancy, but it just means like what symbols you can use with it, like addition and subtraction. Those are so-called operators. Example, the turtle type can be used with function calls that make it draw things. Numeric types like int and float can be used with arithmetic operations, math symbols. And then the value. Well, a variable is supposed to hold a value because otherwise, why did you create it, right? If I create a variable named pi, I may as well put a number in it, right? If I use the word pi without ever having stuck a value in it, it's going to be a syntax error, right? I can't just magically use a variable without having to find it. So, for example, don't type this because it's a syntax error. But if I said, density is equal to weight or mass divided by volume, this is a total syntax error because I never defined mass and I never defined volume. So when I run it, it's going to crash. Boom. It doesn't know what mass is. So it says name mass is not defined. I never defined that variable. So since it doesn't have a value, the compiler can't do anything with it. So a variable must have a value before it can be used. And like I said, in this language, the mere act of creating a variable gives it a value. But it better be good data, right? If I just say mass equals 0 and never fill it in later with a real value, then my density calculation wouldn't work. It's too bad you were having trouble with PyCharm because it really is a better code editor than idle. It'll show you syntax errors as you type them. It'll underline them. Anyways, I have to learn more about it, or at least not use it for turtle programs and can use it elsewhere. I do want to learn why it wasn't working. All right, so all programming languages support these data types. Well, that's a bold claim, but let's run with it. The vast majority of them do. Numbers, right? Because computers run on numbers. Everything's a number to it underneath it all. And strings. Well, that's extraordinarily broad. String is anything not used in math. Oh, well, that's not true. Turtles aren't used in math. A string is just a series of characters, right? Like a name or an address. So, numeric types like int and float are used in math, arithmetic, right? And strings contain characters, right? like names and addresses. Whatever you type in on the keyboard is initially a string. Like keyboard, contain characters like keyboard input. Names, etc. I like the term etc. It leaves it very vague. Alrighty. Means I didn't think of another example besides names and addresses. Song names, right? Album names. Name of your iPhone when you rename your iPhone just from iPhone 10 to, Fred. Whatever. Two types of constants. There are numeric constants, which are also known as literal numeric constants. They contain numbers only, and the number does not change. Alrighty. If we're going through here, the term literal is kind of strange, but that 45 is literally typed into the program. Somebody using my program is not going to be able to change it unless they actually edit it, right? If they don't have the source code to my program, they can't change it from 45, right? Another name for that is hard-coded, right? These 45s are hard-coded into the program. I think back in the days when programs were actually burned onto, proms, they actually were silicon. They weren't loaded into memory. Then hard-coded probably meant that, right? It was right on the silicon. Well, hard-coded means it's not typed in by the user. So if I ask for your name, that's not hard-coded. If I ask for your weight, that's not hard-coded. But all these numbers are hard-coded. And all these numbers are literals. So a literal is data that is hard-coded into the program, meaning that the program must be edited to change it. There are numeric literals and there are string literals. String literals go in quotes. Numeric literals are like t.write 90. The 90 is a literal, right? And they're also called a numeric constant because that 90 would have to, be edited to change. String literals are like, name equals Bob, right? Also known as a string constant. Now, I hate the term constant used for those because I just gave you a different definition for constant up here, right? But these are examples of so-called named constants, right? They're not only a number, but they have a name. So these are examples of named constants. But saying named constants get tedious. Why use two words when you can just use one? So you just call them constants. These literals, you don't really use that term very often unless you're reading a programming book like this one. A string is known as a series of alphanumeric values. Why is it called alphanumeric values? Alphabet, right? Numbers, anything you can type on the keyboard, all the symbols. So we're working with variables. Variables are named memory locations. Well, I gave a bigger definition, or at least I described it by what it contains, right? Maybe I should go up here and add that to my definition that according to the book, right, variables are named memory locations. Back in olden days, before the invention of programming languages like this, you'll actually use numbers in your program saying, okay, store this number in address 10, store this number in address 20, store this number in address 30, right? And that's real dumb because later on you don't know what you stored in 20 and you don't know what you stored in 30. So it's much better to be able to give them names. It'd be like only referring to stuff as by their page and paragraph numbers, or only by their paragraph number rather than chapters, right? Or only by the word number in the book. Want to check the Bible and I tell you to read, words 2000 to 2020, you'd look at me like you're an idiot. So the declaration is a statement that provides its data type its identifier, what I called it a name, and optionally an initial value. Now in Python you have to give it an initial value, but in lots of programming languages you don't. In lots of programming languages you have to give it a type, even if it doesn't have a value. So you declare them like this in those languages, int x. That makes a variable called x that you know later on is going to store a whole number, or string y, right? My program knows that later on I'm going to be storing a string of alphanumeric characters in that variable. Python doesn't work like that. We don't have to explicitly give it a type. Python just figures out the type based on the data stored in it. When I did this, it knew that that's a number, so it knew what type to make the variable. We're going to see lots of references in this textbook to declaring your variables. That's just because in most programming languages you do have to give them types. But some languages you don't. In some languages the type is determined by the data, and that kind of makes them maybe a little bit easier to use. Because, that's extra syntax. If later on I want to give it a value, I say x equals 1 or whatever, but the program knew even before that x was needed to be enough memory to hold an integer. And doing this also told the program that I better not store anything else other than an integer into it. So if I try to store a float or a string or a turtle in it, it's not going to work. So, like I said, the book concerns itself a lot with declarations, and they usually have a separate section in the program for declarations. If we wanted to mimic that, we could just create a whole bunch of variables and set them to 0. Like if I was going to write a program that needed weight, or mass and volume, then I could, at the top of my program, not that this is the top of the program, right? But I could create a declarations section, and I could say, in those languages I would say float space mass equals 90. This one doesn't need that float word, so I just say, but I'm going to say mass is equal to 0 and volume is equal to 0, and then later on I would input that, right? I would have some kind of code that would input mass, right? Then later input mass, or assign a value to mass and volume. That's kind of classical programming. Some people like to declare all their variables up at the top of the program or the module, because then when you open up the file, you kind of get an idea of what that program is supposed to do. If I see a reference to something that says name, phone number, and address, I get kind of an idea of what this module concerns itself. We don't have to do that in Python because we can declare variables on the fly. If I want to declare a name right here, name equals Fred, right? I can, right? There's no reason to, right? But I could, right? Which is why we can get away with doing something where halfway down the program we say density equals mass divided by volume without already having predefined that variable. So the book shows declaring your variables at the top of the program. Or I should say near the top of the program. Usually there's a comment block, right? So here we see it in the pseudocode. Declarations, num, my number, num, my answer. Zoom in on that. Blurry. Well, anyways, the book is being even vague, more vague than calling it an int and a float. If I was going to bother putting declarations in pseudocode, I would probably use the words int and float rather than just that generic num, because you'd need to know that when you actually programmed it. And then here they're showing that in a flowchart. I totally don't care if you skip declaring variables and putting it in your pseudocode and putting it in a flowchart. And I'm sorry to veer from the book. I should be hardcore and say you got to do it exactly like the book. But if you don't have to do it in Python, then why force you to do it? Just remember that in some languages you do have to declare your variables, but even in those you don't have to declare them up at the top. So there are numeric variables that can hold digits. Remember what I said? A type declares what it holds and what operations can be done on it. So it can perform math operations on it. A string variable can hold text, letters of the alphabet, special characters such as punctuation mark. And then there's the idea of type safety. Python does not have type safety. Part of it being more flexible, where you could store a string in it at first and then later on convert it into a float. And we've kind of done that, right? Type safety prevents storing the wrong kind of data in a variable. In languages that support it, so you can declare a variable as one type, and that forbids data of another type being put in it. And some would argue that that makes your code, less prone to errors or whatever. You don't accidentally override a variable with the wrong kind of data. Python doesn't have that. Smiley face. Which is why we can do things like x equals input. X is a string at this point. And then x equals float x. X is now a number. That's not possible in those strictly typed languages with type safety. It's just kind of handy. We wouldn't have to do it like that, right? We could say x is equal to input and then y is equal to that, right? Which is how you do it in those other languages. But I kind of like using the same variable name, right? If I type in mass equals input and then I can convert mass to a number later on to use it, then I'm still using the same word for it. It's very common in Python. So the above code would not be possible in languages like Java and C++ that perform type safety checks. The technical term for that is that they are strongly typed. So the identifier, that's the variable's name. You should choose reasonable names for your variables. Like what if instead of using name and address and phone number and patient height and patient weight and last appointment and insurance information or whatever, I just said X1 and X2 and X3 and X4 and X5. That's totally legal, right? Your program would work just fine as long as you remembered what all those variables are for. But when you went back to edit it, or when you had to edit somebody's code that was written like that, you'd start cursing them, or you'd curse yourself, right? Because you wouldn't know what X3 and X27 meant, right? You wouldn't know that one of them was supposed to be the patient's hair color or something like that, right? So you try to use good variable names. Now, since I'm typing in multiple lines of code, I'm just going to go back to the green quote, quote, quote. Variables have names, technically known as identifiers. Choose good variable names. Like height rather than age. Okay, I'm going to be using H rather than height a lot of the time just because it's easy for y'all to type and you don't switch the E's and the I's and stuff like that. But if you were going to write a professional program, or if I would use a better variable names. Avoid single letter variable names except for counters. If you're just going to count from 1 to 10, it's kind of okay to say, well, that's X. I'm going to count from 1 to 10. In this class, I demonstrate a lot with single letter variable names just because they're easy to type. And if you look up a formula, you know, for like the surface area of a cylinder, then it's going to be expressed in letters, right? It's going to show you that it's r squared plus, you know, h times pi or something like that. So for math stuff, I certainly don't mind storing that data in single letters. But technically, you should do things like height, or even better, patient height. This is a very common naming scheme where you use capital letters to break up the words. But I use underscores here so that you don't have to type in capital letters. Why? Because sometimes you would type caps and sometimes not. That's just my experience from students, and it's not because you're dumb. It's just because it's real hard to see up here whether I used an uppercase H or a lowercase, and you might not hit it every single time. We're not all trained typists, right? So anyways, I use underscores. They're considered old-fashioned, but who cares, right? We can do them anyways. Rather than H, or heaven forbid, you know, X1, or something like that. You don't need to abbreviate, right? You could abbreviate height, HT, right? It's probably better than H, certainly a lot better than just calling your variables X1, X2, and X3. For math formulas, ain't nothing wrong with using single letter variable names, right? For the code we're writing. We can use single letter variable names, but if you want to impress me, if you're going to do density is equal to mass over volume, that's cooler than doing D is equal to M over V. Single letter. I'm almost going into too much detail over the notes, but I'd really like for you to go back and reread them, you know, like at least once, right? We're not just typing them in because we like to exercise our fingers. Variable names are case sensitive, right? So if I typed in patient height with an uppercase H, when I input it, it better keep that uppercase H everywhere I refer to it. There are rules for variable declarations. Almost every language follows the same rules. You can use letters, both upper and lower. You can use underscores. A few languages let you use dollar signs, but I'm not going to mention it because most of them don't. And you can use digits. Cannot begin with a digit. And as a side effect of these being the specific rules, cannot have spaces. So I would not type in patient space height. So patient space height equals 60 is totally wrong, right? Well, what about the fact that I don't know what the height is measured in, right? Or the volume, or, you know, the length or whatever. It could be useful to put the units in the type, right? So like height, inches, right? Or temperature in F, right, for Fahrenheit. That kind of thing. Consider expressing the units to your variables' names. All right, so based on homework, or the homework coming up from this, write a program that asks the user for the temperature in Fahrenheit. I don't even know how to spell that. converts it to Celsius, and displays the result. Now, I'm not going to give you the formula because you can Google it. But as I say this 20 times per semester, it's not a math class. If you're stuck, text me, and I'll write down the formula. I'll send it back to you. Text me if you need the formula. You get to pick the variable names. Avoid, in this case, single letter variable names. So rather than just F and C for Fahrenheit and Celsius, come up with something cooler than that. Alrighty. Sorry for scrolling up and down. And as always, I'll mention that I post the homework instructions, so it's not like you have to type them all in, but I know that some people like to anyways. So like back in the 60s and stuff, you couldn't mix your lowercase and uppercase letters because the compilers were more primitive, right? You didn't have, megabytes of memory in order to run your programs. And so people who invented languages would come up with rules like functions and stuff like that are all declared in lowercase, and variables are all declared in uppercase, right? And so when you were looking through the code and you saw an uppercase letter, or the program looked through it and was trying to compile it, it would know, oh, that's a variable name. Some languages, back in the 70s or whatever, would limit you to 8 characters, right? So then people did go nuts with their abbreviations, trying to get, their variable names to be less than 8 characters long. Alrighty. I'll bring that back up after we lecture a little more if you need more typing time. So variable names must be one word. Wait, I can think of something we ought to do right now. Name.